We're trying to test whether a new low-fat diet actually helps obese people lose weight. 100 randomly assigned people are assigned to group 1 and put on the low-fat diet. Another 100 randomly assigned obese people are assigned to group 2 and put on a diet of approximately the same amount of food, but not as low in fat. So group 2 is the control, just the no diet. Group 1 is the low fat group, to see if it actually works. After 4 months, the mean weight loss was 9.31 pounds for group 1. So let me write this down. The mean weight loss for group 1, let me make it very clear. So the low fat group, the mean weight loss was 9.31 pounds. So our sample mean for group 1 is 9.31 pounds with a sample standard deviation of 4.67. And both of these are obviously very easy to calculate from the actual data. And then for our control group, the sample mean, and 7.40 pounds for group 2. So our sample mean here for the control is 7.40 with a sample standard deviation of 4.04 pounds. And now if we just look at it superficially, it looks like the low-fat group lost more weight than, just based on our samples, than the control group. Right? If we take the difference of them, so if we take the difference of the low-fat group from, or between the low-fat group and the control group, we get, what is it? It's 9.31 minus 7.40 minus 7.40 is equal to, now let's get the calculator out. So then we have 9.31 minus 7.4. So it's 1.91. So it's 1.91. So the difference of our samples is 1.91. So just based on what we see, it says, hey, maybe you lose an incremental 1.91 pounds every 4 months if you are on this diet. And what we want to do in this video is to get a 95% confidence interval around this number to see that are all that in that 95% confidence interval, maybe do we always lose weight? Or is there a chance that we can actually go the other way with the low-fat diet? So really just this video, 95% confidence interval. In the next video, we'll actually do a hypothesis test using this same data. And now to do a 95% confidence interval, let's think about the distribution that we're thinking about. So let's look at the distribution. Of course, we're going to think about the distribution that we're thinking about. We want to think about the distribution of the difference of the means. So it's going to have some true mean here. It's going to have some true mean over here, which is the mean of the difference of the sample means. Actually, let me write that. It's not a y, it's an x1 and x2. So it's the sample mean of x1 minus the sample mean of x2. And then this distribution right here is going to have some standard deviation. It's going to have some standard deviation. So it's the standard deviation of the distribution of x, of the mean of x1 minus the sample mean of x2. It's going to have some standard deviation here. And we want to make an inference about this. Or I guess the best way to think about it, we want to get a 95% confidence interval based on our sample. We want to create an interval around this where we are confident that there's a 95% chance that this true mean, the true mean of the differences, lies within that interval. And to do that, let's just think of it the other way. How can we create a 95% confidence? How can we create a 95% interval around this, around the mean, where we are 95% sure, or construct an interval around this, where we're 95% sure that any sample from this distribution, and this is one of those samples, that we're 95%, that there's a 95% chance that we will select from this region right over here. So we care about a 95% region right over here. So how many standard deviations do we have to go in each direction? And to do that, we just have to look at a z-table. And just remember, if we have 95% in the middle right over here, we're going to have 2.5% over here, and we're going to have 2.5% over here. We have to have 5% split between these two symmetric tails. So when we look at a z-table, we want the critical z value that they give right over here. And we have to be careful here. We're not going to look up 95% because the z-table gives us the cumulative probability up to that critical z-value. So the z-table is going to be interpreted like this. So there's going to be some z-value right over here where we have 2.5% above it. 2.5, the probability of getting a more extreme result, or a z-score above that, is 2.5%. And the probability of getting one below that is going to be 97.5%. 97.5%. But if we can find whatever z-value this is right over here, it's going to be the same z-value as that. Instead of thinking about it in terms of a one-tailed scenario, we're going to think of it in a two-tailed scenario. So let's look it up for 97.5%. 97.5% on our z-table. Let's see, we have 97 right here. This is 0.975, or 97.5. And this gives us a z-value of 1.96. So this is z is equal to 1.96. Or only 2.5% of the results, or of the samples from this population, are going to be more than 1.96 standard deviations away from the mean. So this critical z-value right here is 1.96 standard deviations. Or this is 1.96 times the standard deviation of x1 minus x2. And then this right here is going to be negative 1.96 times the same thing. Let me write that. So this right here, it's symmetric. This distance is going to be the same as that distance. So this is negative 1.96 times the standard deviation of this distribution. And if there's a 95% chance, so let's put it this way. There's a 95% chance, there is a 95% chance that our mean, or I guess we could say that our sample that we got from our distribution, this sample is a difference of these other samples. There's a 95% chance that 1.91 lies within, or let me just write it, is within this distance, is within 1.96 times the standard deviation of that distribution. So you could view it as a standard error of this statistic. So x1 minus x2. Or we can say that there is a 95, let me finish that sentence. There's a 95% chance that 1.91, which is the sample statistic, or the statistic that we got, is within 1.96 times the standard deviation of this distribution of the mean of the distribution, of the true mean of the distribution. Or we could say it the other way around. There's a 95% chance. There is a 95% chance that the true mean of the distribution, is within 1.96 times the standard deviation of the distribution of 1.91. These are equivalent statements. If I say I'm within 3 feet of you, that's equivalent to saying you're within 3 feet of me. That's all that's saying. But when we construct it this way, it becomes pretty clear how do we actually construct the confidence interval. We just have to figure out what this distance right over here is. And to figure out what that distance is, we're going to have to figure out what the standard deviation of this distribution is. Well, the standard deviation of the differences of the sample means is going to be equal to, and we saw this in the last video. In fact, I think I have it right at the bottom here. It's going to be equal to the square root. It's going to be equal to the square root of the variances of each of those distributions, right? Or the variance of this distribution is going to be equal to the sum. Let me write it over this way, right over here. So the variance, let me write it right over here. The variance, I'll kind of prove it. The variance of the means, or the variance of our distribution, is going to be equal to the sum of the variances of each of these sampling distributions. And we know that the variance of each of these sampling distributions is equal to, the variance of this sampling distribution is equal to the variance of the population distribution, the variance of the population distribution divided by our sample size, and our sample size in this case is 100, and the variance of this sampling distribution for our control, let me do this in a new color, for our control is going to be equal to the variance of the population distribution for the control divided by its sample size. And since we don't know what these are, we can approximate them, especially because our n is greater than 30 for both circumstances. We can approximate these with our sample variances for each of these distributions. So let me make this clear. Our sample variances for each of these distributions. So this is going to be our sample variance 1 or actually our sample standard deviation 1 squared, which is the sample variance for that distribution, over 100, plus my sample standard deviation for the control squared, which is the sample variance. Standard deviation squared is just the variance, divided by 100. And this will give us the variance. This will give us the variance for this distribution. And if we want the standard deviation, we just take the square roots of both sides. If we want the if we want the standard deviation of this distribution right here, this is the variance right now, so we just need to take the square root. So let's calculate this. We actually know these values. S1, our sample standard deviation for group 1 is 4.67. We wrote it right here as well. It's 4.67 and 4.04. So this is 4.67, and this number right here is 4.04. The s is 4.67. We're going to have to square it. And the s2 is 4.04. We're going to have to square it. So let's calculate that. So we're going to take the square root of 4.67 squared divided by 100 plus 4.04 squared divided by 100, and then close the parentheses, and we get 0.617. So this is equal to, let me write it right here, this is going to be equal to 0.617. So if we go back up over here, we calculated the standard deviation of this distribution to be 0.617. So now we can actually calculate our interval, because this is going to be 0.617. So if you want 1.96 times that, so we get 1.96 times that 0.617. I'll just write the answer we just got. So we get 1.21. So this number right here. This number right here is 1.21. So the 95% confidence interval is going to be the difference of our means, 1.91, plus or minus this number, 1.21. So what's our confidence interval? If we subtract it, so the low end of our confidence interval, and I'm running out of space, the low end, 1.91 minus 1.21 is just, what is that? That's just 0.7. So the low end is 0.7. And then the high end, 1.91 plus 1.21, what is that? That's 2.12. 2.12. Let me just make sure that my brain sometimes doesn't work properly when I'm making these videos. 3.12. Oh, good thing I redid it. 3.12, of course. Yeah, 3.12. So it is 3.12. So, and just be clear, there's not a pure 95% chance that the true difference of the true means lies in this. We are just confident that there's a 95% chance. And we always have to put that little confidence there, because remember, we didn't actually know the population standard deviations or the population variances. We estimated them with our sample. And because of that, we don't know that it's an exact probability. We just have to say we're confident that it's a 95% probability. And that's why it's really we just say it's a confidence interval. It's not a pure probability. But it's a pretty neat result. We have this 95% confidence interval. So we're confident that there's a 95% chance that the true difference of these two samples, and remember, the sample means, the means of the sample, the difference between the, let me make it very clear. The difference between the means of the sample is, or let me put it, the sample means, or the expected value of the sample means is actually the same thing as the expected value of the populations. And so what this is giving us is actually a confidence interval for the true difference between the populations. If you were to give every possible person diet 1 and every possible person diet 2, this is giving us a confidence interval for the true population means. And so when you look at this, it looks like diet 1 actually does do something, because in any case, even at the low end of the confidence interval, you still have a greater weight loss than diet 2. Hopefully that doesn't confuse you too much. In the next video, we're actually going to do a hypothesis test with the same data.